All right, by this point, we should be able to perform each of the different stoichiometric conversions that we've been doing throughout Unit 7. At this point, we're going to kind of put them into a practical application, if you will. We know how to do them, but this is going to be kind of putting into a larger story where we could actually problem solve and get some more information out of just these conversions. So this is called limiting reactants. Now, a limiting reactant is the reactant. Again, as you guys know, a reactant is on the left side of the table. The reactant that produces the least amount of product. Okay? And again, why that is because in a chemical reaction, if you were to have, say, an infinite number of reactants, then the reaction, in theory, would kind of go on forever. That's not exactly the case, but for now, that makes sense, right? If you had enough reactants, then the reaction should be able to go on pretty much forever. But in the real world, one of the reactants is going to be consumed. It's going to be all used up. And at that point, the reaction cannot go any further, and it's going to grind to a halt, and it's going to stop. At that point, the reaction is finished. The reactant that has been consumed and is all gone, we call the limiting reactant because it has limited the reaction and has stopped it. On the other hand, any other reactant that is still present is going to be called the excess reactant. So this is the reactant, again, that could produce more product. Now again, it could, but it can't because again, the reaction's finished because the limiting reactant has been all used up. But again, there would be more of the excess reactant and so that it could go on, but it just can't. The reaction is finished again. So how do I determine which is a limiting reactant? We're gonna have to do two different calculations. They're gonna start from different points, but we're gonna solve for the same product. We're gonna compare to see which one would make the least amount of product. Whichever makes the least amount of product is going to be our limiting reactant. So I'm going to say whichever reactant produces, sorry, my pen messes up a little bit, the least amount of product. That will be what the limiting reactant is. The one that would produce more, in theory, would be considered our excess because it could make more if it had enough of the other reactant. Now, how do I identify a problem as a limiting reactant problem? I want to draw your attention down to number one. If you look at number one, we have this many moles of barium chloride and this many moles of sulfuric acid. At no point in Unit 7 have we ever been given a problem where we have two starting points. We're typically given one thing, number, unit, and compound to begin with, and they tell us to convert into this. So it's from this to this. There is no other way. In a limiting reactant problem, you're going to be given two starting points because we have to do two reactions, or excuse me, two calculations in order to compare the same amount of product. So that's how we're going to be able to figure that out. So we're going to be given two starting points, if you will. And by starting points, what I mean by, again, is this and this, okay? So whenever you see that, you know automatically you're gonna have to do two calculations because we're gonna try to find which one makes the least amount of product. And again, that's the amount of product that would actually be created, and the reactant that made that smaller amount of product is going to be our limiting reactant. All right, so let's go ahead and try number one. So in number one, the first thing I wanna do is go ahead and just get this thing balanced because why not, right? So I have two chlorines and two hydrogens. So that means it's going to be a 2. So that's going to be a 1 to 1 to 1 to 2 ratio on that balanced equation. So what we're going to have here is we're going to have two starting points. We're going to have 6.00 moles of barium chloride. And our other starting point in the problem is we have 5.00 moles of sulfuric acid. Again, again, where I'm getting that from is right here and right there. All right, so then what we have is it's going to ask how many moles of precipitate will precipitate. The precipitate is going to be this one. So we need to convert both of them into moles of barium sulfate. Why moles? Because it says moles. So, oops, I'm sorry, I'm too busy talking and not thinking. That's barium chloride, again, because that's going to cancel out, right? So that's got to be the same. This is going to be the moles of my product, barium sulfate. Right? And again, going through from the balanced chemical equation, barium chloride is right here, so it's a 1. Barium sulfate is right here, so that's also a 1. I'm going to go ahead and wait to do my calculation until I get the other one set up. So my other one, I'm going to put moles of my starting reactant, H2SO4. That way that cancels with this. And again, I'm going to put the exact same product on the top because that's what we're solving for. We want to solve for the same exact thing. Now again, for the bottom number, sulfuric acid is right there. That's a 1. Barium sulfate is right there. The number in the front is a 1. All right, so to solve this, this actually looks out quite nicely. 6 times 1 divided by 1 is still going to be 6.00 moles of our product, BaSO4. And at the bottom, we have 5 times 1 divided by 5. Again, that's also going to be 5 moles of barium sulfate. So again, the math was super easy because, again, it's a 1 to 1 to 1 to 2 ratio, but we didn't even need the hydrochloric acid. That wasn't really involved in the problem. So what that tells me is that if we started with 6 moles of barium chloride, we should be able to make 6 moles of barium sulfate, but we wouldn't because the 5 moles of sulfuric acid would be consumed. Why do I know that? Because this is the smaller of the two products. 5 moles is smaller than 6 moles. Therefore, the amount that we would actually be able to make in this equation or this reaction is 5 moles of barium sulfate. After that point, the reaction would finish. So what we need to figure out is what is the limiting reagent. The limiting reagent would be the one that makes the smaller. So here's the smaller answer. So it's going to be that which made the smaller numbers. That's H2SO4. The excess reagent is the one that would make the larger number. Here's the larger number, right? The compound that made the larger number is right there. It's BaCl2. So we're going to have some BaCl2 left over after the reaction is finished because the H2SO4 will be consumed, and that's when the reaction is finished. So we have answered the first question. How many moles of precipitate will precipitate? Again, the answer to that question is 5 because it's the smaller of the two numbers. And we've also went ahead and identified the limiting reactant, which is H2SO4, and the excess reactant, which is BaCl2. We have one more question, and the other question says, how many moles of excess reactant remain? So I'm going to go ahead and change my colors. So what we need to do here is we're going to figure out how much of our excess, which is this, remains. We're going to take these two numbers here and we're going to subtract them. So I'm going to do 6.00 minus 5.00, and of course that is 1.00 moles. Okay, so I'm going to take that number and I'm going to start another conversion, 1.00 moles of our product, which is BaSO4. I'm going to go ahead and convert out of moles. I'm going basically backwards from my moles of my product back into my moles of my excess reactant. So moles, our excess is BaCl2. Again, from the chemical equation, BaSO4 is right here. It's a 1. BaCl2 is right there. It's also a 1. So again, not surprisingly, 1 times 1 divided by 1 is still going to be 1 mole of our excess reactant. All right, so to put that in regular English, what all of this tells us is that if we started with 6 moles of barium chloride and 5 moles of sulfuric acid, the reaction would stop after we created 5 moles of our product, barium sulfate. At that point, the reaction is finished. How much of the other excess barium chloride would we be left with? That would be exactly 1 mole. Now, some of this hopefully seems kind of obvious, and that's basically because the molar ratios, if you look down the center of your screen, all of these molar ratios are 1 to 1. So that really, again, made the math very, very easy. So we're going to do number 2. Number 2 is going to be very similar as far as pattern. The math's going to be almost as easy, except our mole ratios will not be 1. So let's try it. Number two, what we need to do first now, of course, is balance the chemical equation. So whenever we have 2 and 3 oxygens, this needs to be 3, this needs to be 2. That gives me 6 oxygens on both sides. My aluminums now have been quadrupled. So there we go. Now my equation is balanced. All right, so what we're given to start with is we are given 3 moles of aluminum. And we're also given 3 moles, or 3.0, it's really just 3, isn't it? 3 moles of oxygen. All right, what they want us to solve for is moles of the excess reagent or reactant remaining. I'm going to put moles of aluminum in order to cancel that out, right? And then I'm going to put moles of our product. Again, we only have one product, so clearly let's solve for Al2O3. There's nothing else to solve for, right? Then again, using my mole ratios, the aluminum is right here, so that's going to be a 4. The aluminum oxide is right there, so that's going to be a 2. All right, then that means to do this calculation would be 3 times 2, which is 6, divided by 4 will give us 1.5 moles of our product, aluminum oxide. For the next one, we're going to do basically the same thing. Moles of oxygen needs to move down here in order to cancel that out. Cancels. Then we're going to go into moles of our same product, aluminum oxide, the same product as we did before. So on the bottom, we have oxygen. There's oxygen. It's going to be a 3. And of course, just like before, there's aluminum oxide. It's still going to be a 2. So when we do the math, that's going to be 3 times 2, which is 6, divided by 3 gives us 2 moles of our product, aluminum oxide. So the question says, first of all, identify the limiting reactant. In order to do that, we need to figure out which product would actually be able to make. The answer is this one because, again, simply it is the smaller of the two. We would only be able to make 1.5 moles of aluminum oxide. After that, we're going to run out of something. What we're going to run out of is our limiting reactant, which in this case is that produced the smaller number. The excess reagent or reactant is, again, here's the bigger number. It's going to be the one that made the bigger number, in this case, oxygen. All right, so now we have identified the limiting reactant, which is what they asked us for, which is aluminum. Then they want us to solve, all right, this is the second part. We need to solve for the moles of excess reactant remaining. So just like before, I'm going to take these two numbers and I'm going to subtract them. So 2 minus 1.5 gives me 0.5 moles. So again, I'm going to start another conversion, going from moles of our product, which is Al2O3, and go back into our excess reactant. Remember, our excess is aluminum, or excuse me, is oxygen. So I'm going to move my moles of aluminum oxide down here to cancel that out. Then I'm going to move into moles of our excess reactant, which we just said is oxygen. All right, then using our balanced chemical equation, aluminum oxide is right here. The number in the front is a 2. Moles of oxygen, there it is. The number in the front is a 3. So all I have to do now is the math. 0.5 times 3 is 1.5. 1.5 divided by 2 gives me 0.75 moles of oxygen. So there's our second answer. So again, to translate this into regular English, if we were given 3 moles of both aluminum and oxygen, equal amounts, 3 moles of each, and we reacted them together in a synthesis reaction to make aluminum oxide, we would stop after making only 1.5 moles of aluminum oxide. Why? Because we ran out of aluminum. The aluminum was all consumed. But we would be left with 1.5 moles of aluminum oxide, but we would also be left with 0.75 moles of oxygen gas remaining, unreacted, excess, okay? So that's how we do number 2. Again, it's a little bit better than number 1 in that it's not as obvious. Because again, if you subtract 2 minus 1.5, what we originally got was 0.5. But when you convert that into oxygen, it actually comes out to be something different. Again, only because the chemical equation is a 4 to 3 to 2 ratio. That makes it a little less obvious, unlike number 1. Number 3, again, is going to be a little bit more advanced in that is a mass to mass problem. A mass to mass, remember, is a 3-step. So what we need to do first is balance our chemical equation. I'm going to go ahead and put a 2 there, a 3 there. Nope, that's not right. A 6 there, a 3 there, and a 2 there. There we go. That's a balanced chemical equation. Again, I'm going to do that part kind of quick because I want to spend my time on the new stuff, which is the limiting reactant. So our two starting points are going to be 16.2 grams, not moles, but grams of aluminum. And our other starting point is 61.0 grams of hydrochloric acid. So again, this is a mass to mass. So we got to get out of grams of aluminum into moles of aluminum. Then we're going to get out of moles of aluminum and into moles of our product. Now, I got to pause. What product? It says how many grams of gas are produced? Well, this is the gas. Hydrogen's a gas. So it's going to be H2. Aluminum chloride is not a gas. All right, then I'm going to get out of moles of hydrogen and finally into grams of hydrogen. Just to remind you guys, if you look at the numerator, if you look at the top number, it's going to be grams to moles to moles to grams, right? Grams of A to moles of A to moles of B, grams of B, just to remind you guys the pattern and how that works. All right, now we're going to do the numbers. So whenever we have moles on top of grams, the moles is going to be 1. Grams comes from the periodic table. That is just simply aluminum. So that's going to be 26.982. I'm going to jump all the way over to the right. Whenever we have grams on top of moles, the moles is 1. The grams comes from the periodic table. That's called molar mass. The hydrogen is 1.008 from the periodic table times 2. So that's going to be 2.016. Then the middle part is our mole to mole. On the bottom, we have aluminum. There it is. The number in the front is a 2. On the top, we have H2. There it is. The number on the front is a 3. So all we need to do now is calculate that, but I'm going to go ahead and jump to the bottom one so I can just go ahead and do everything all at the same time. Here is our grams of hydrochloric acid because we need to cancel that out, right? Then we're going to go into moles of hydrochloric acid. Once we're in moles of hydrochloric acid, this is our mole to mole step, our conversion from hydrochloric acid into the exact same product as we did before. Then we're going to get out of moles of hydrogen and into grams of hydrogen. Okay, remember these will cancel, these will cancel, these will cancel, 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 cancel. All right, so again, the numbers, whenever we have moles on top of grams, the moles is going to be 1. The grams comes from the periodic table. I'm going to go ahead and calculate this really quickly. So 1.008 plus the mass of chlorine, which is 35.453. I'm going to add those together and I get 36.461. Again, I got that from the periodic table. On the far right, again, it's going to be 1 mole under the mass of hydrogen times 2, which is 2.016. Then again, I'm going to do my molar conversion step. On the bottom, I have HCl. There's HCl. So the number is going to be a 6. On the top, we have H2. There's H2. The number in the front is a 3. Now, you're probably thinking, holy crap, that's a lot of work. What I want to point out to you guys really quickly is a lot of this is actually repetitive. Take a look at this right here. Take a look at that. Those are basically the exact, or not basically, they are exactly the same. And the reason is because we're solving for the exact same product. So really the only thing different is the molar mass on the bottom left and the molar conversion on the very bottom center. So it's not as bad as it sounds. Honestly, you could just kind of copy part of the top one down into the bottom one. All right, so I'm gonna pick up my calculator. I'm gonna go ahead and calculate all this. So 16.2 times 1 times 3 times 2.016 divided by 26.982 divided by 2 equals, my answer is 1.816 grams of H2. Then I'm going to do my second one, which is 61.0 times 1 times 3 times 2.016 divided by 36.461 divided by 6. Oops, I almost hit multiply. Divide by 1. And that gives me 1.686 0.6 grams of H2. Notice they're both for H2 because we're trying to compare the same product, right? Don't solve for different products because you're going to be wasting your time. So again, the question is how many grams are produced? Again, I look at these two answers. This one is the smaller one. That is the amount of grams that would be produced. So starting with those masses of aluminum and hydrochloric acid, we would only produce 1.686 grams of hydrogen. After that, we would run out of course, our limiting reactant, which in this case is this one, which is hydrochloric acid, because it produced a smaller amount of product. And our excess reagent would be this one, because it made the larger amount of product. Even though it didn't ask me for that, I want to go ahead and identify that. So there's number 3. Again, that is with a mass to mass 3-step. We basically just went from grams of whatever they gave us, the 2 reactants, and we solved for grams of the exact same product. We compared the 2 answers. Whichever is the smaller is the amount of product that would be formed. The larger number could not be formed, remember, because the limiting reactant would be consumed. All right, on to the very last one. The very last one, we have number 4. I'm going to give myself a little more space. Number 4, what we have here is, of course, an equation. So let's go ahead and balance that one first. All right, so to balance this chemical equation, let's see, we have one O, we have one Na. Our H's are not balanced, so I'm going to put a 2 there. That gives me twice the number of H's or O's. So now we have 4 H's. That gives us 4 H's, 2 O's, and 2 Na's. There we go. That's balanced. All right, now again, let's go ahead and try the equation. So calculate the mass of hydrogen that is produced. So we've given 2 things, 40.0 grams of sodium, and we're also given 36.0 grams of water. So again, we're going to convert out of grams of sodium into moles of sodium. Hopefully you guys know this pattern by now. I'm just following the pattern. Then out of moles of sodium into moles of our product. Again, they want to know the mass of hydrogen gas. So that's H2. And we get out of moles of H2 into grams of H2. All right. Then again, whenever we have moles on top of grams, the mole's going to be 1. Grams comes from the periodic table, which in this case is only one of them. So it's 22.990. On the far right, we have moles under grams. So the moles is going to be 1. Grams comes from the periodic table. Again, there are 2 hydrogens. That's a decimal, sorry. And then in the middle, we have our balanced chemical equation. So on the bottom, I have sodium. There it is. So the number in the front is a 2. Come on. There we go. And on the top, what we have is H2. So what we're going to have here is H2 is right there. So it's going to be a 1. All right, I'm going to go ahead and finish out the other one. That way I can calculate both at the same time. Just make it a little bit easier for myself. I'm going to put grams of H2 down here to cancel that out. Then I go into moles of H2O, sorry. Then I'm going to go out of moles of H2O into moles of H2. All right, again, we're going to go out of moles of H2 into grams of H2. Again, remember that these 2 parts right here are identical, right? So in theory, I could just go ahead and copy that, which is exactly what I'm going to do. So I'm going to put a 1 mole here, and I'm going to go ahead and put 2.016, and I'm going to put 1 there, because again, those are going to be the same. All I need to do now is figure out my mole ratio for water. It is right here. The number in the front is a 2. All right, and then we need the molar mass of water. So the mass of water is 15.999, that's the oxygen, plus 2 hydrogens, which gets me 18.015, and again, that's equal to 1 mole. All right, now that I have all that, let me go ahead and calculate the 2 numbers. So I have 40.0 times 1 times 1 times 2.016 divided by 22.990 divided by 2 divided by 1 equals, I get 1.754 grams of hydrogen gas. On the bottom, 36.0 times 1 times 1 times 2.016 divided by 18.015 divided by 2 divided by 1 equals 2.014 grams of the same product hydrogen gas. All right, so again, we need to identify the limiting reactant. So again, this is the smaller of the two. So that's all the amount of hydrogen gas we'd be able to form. Therefore, the limiting reactant is the one that produced that smaller number, which in this case is sodium. The excess reagent is the one that made the larger number, which in this case is water. So our excess reagent is water. So there's part B. All right, so the last one, calculate the mass of the excess reactant that remains when the reaction is complete. Okay, so we need to figure out how much of our excess is left over when all is said and done. So I'm going to take these two numbers and I'm going to subtract them. 2.014, I'm basically finding the difference. And whenever someone says difference in English, in math, they mean subtract. So I'm going to go ahead and take 2.014 minus 1.754, and what I get is 0.26. All right, so 0.26 grams of our product. Again, I'm going to go ahead and do that. Start another, oops, let me try it again. 0.26, that's a 0, grams of H2. All right, I'm going to convert out of grams of H2 into moles of H2. Then I'm going to convert out of moles of H2 into moles of our excess reagent. Again, which one is our excess reagent? Well, we already found out it's H2O. So moles of H2O. And I'm going to get out of moles of H2O into grams of H2O. All right, so again, moles over grams, moles is 1, grams comes from the periodic table. We've already determined right here that the molar mass of two H's is 0.0 or 2.016. On the very far right, 1 mole under grams is 1. The grams would come from the periodic table. We already determined that the mass of water is 0.185, again, because we found it right there. All right, then again, in the middle, what we have is our ratio. Hydrogen on the bottom, there it is, it's 1. Water on the top, there it is, it's 2. All right, and then I'm going to pick up my calculator and solve. 0.26 times 1 times 2 times 18.015 divided by 2.016 divided by 1 equals 4, oops, let me change that color. Gotta get my color scheme all set. 4.647 grams of our excess reagent, which is water. All right, so yes, that looks like a lot of work. Yes, that I just did 3 mass to mass conversions, but what I also want to point out to you guys real quick is there's another pattern that if you spot, it makes it a lot easier. Notice this right here in comparison to this right here. So the reason why I'm highlighting those two is because the top one is going from moles of water into grams of hydrogen. And on the bottom, you're going from moles of hydrogen into grams of water. They're the exact same thing, just switched and flipped. Okay, so if I've already done the top one, the bottom one is the exact same thing. You just flip it and switch it. Okay, again, notice on the top, we have 1 over 18.015. On the bottom, we have 18.015 over 1. On the top right, we have 2.016 over 1. On the bottom left, we have 1 over 2.016. It's the exact same thing. Again, just you switch it over here and you flip it like that. That's all there is to it. It makes it a lot easier. You don't have to reinvent the wheel. You just have to follow the pattern if you could recognize the patterns. All right. All that being said, let's put this into English. If we started with 40 grams of sodium and 36 grams of water, and we reacted them in a single replacement reaction to make sodium hydroxide and hydrogen gas, we would only be able to make 1.754 grams of hydrogen gas. After that, the reaction would stop only because we ran out of sodium. We would have extra water, and the exact amount of extra water we would have would be 4.647 grams of water. That much would remain unreacted. Okay. All right, so for 4D, it's talking about something called percent yield. You'll notice that's right below. So I'm going to skip that for now, and we'll do percent yield next. All right, guys, again, as always, thank you very much for watching, and I will see you again very soon.